So we were looking at eligibility traces. Right, we looked at TD lambda. So what would be the next step to go? Naturally would be to look at control, right. So after looking at TD lambda, which is essentially a estimation method, so we have to look at control. So the easiest to think about in terms of control is version of SARSA that will use an eligibility trace, right. So what does it mean to have an eligibility trace in SARSA? Yeah, so the backward view is kind of easy to see where we are going with, right. So backward view in fact is almost like TD lambda. So essentially what I do now is I introduce a eligibility trace for, so I introduce an eligibility trace for state comma action pair, just like you went from state values you go to action values for Q learning and SARSA, so you go to state comma action pairs. You have an eligibility trace like this, right, and how do I update it? Right, this is exactly what we did there. So this is kind of your accumulating trace. So if you want replacing trace, what do you do? Okay. So there is one other thing which you have to be careful about when you are talking about eligibility traces on state action pairs, right. Suppose I am in some state, yes, right. This is action A1, this is action A2, I do not need even this. Okay. This is action A2, that is action A1, this has a 0 reward, right, and then I have a policy right now that keeps taking action A1 many times and then finally takes action A2 and gets a reward of +1, right. If I am using accumulating traces, so what will happen is every time I go around this loop I will keep adding 1, right. The first time I go I will have 1, right, and the next time I go I will have 1 plus gamma lambda, the next time I go I will have 1 plus gamma lambda, no, this into gamma lambda, right. So I will have gamma lambda plus gamma lambda the whole squared plus 1, okay, I will keep going there. At some I will basically my trace for this will be some number of times gamma lambda power t, right, t running from 1 to some time some k, right. Depending on the exact values of gamma lambda, this number can be much larger than 1, right. So I have gamma lambda plus gamma lambda squared, so forth. So yeah, it is decaying, right, but you think about every time I am upping it by 1, right. So it will be a number larger than 1, could be a number larger than 1, and what will be the trace of A2? When I finally take A2 it will be 1, right, and which action you think is going to get the higher fraction of this plus 1? A1 will get updated more than A2, right. So what will happen next time I come to state is I will be more likely to take A1, right. Again I will do this a few times and then I will take A2 and again A1 will get rewarded. Yes. So even if I use replacing trace, what will happen? That guy will get gamma lambda, okay. It could still be a large number, right. So the rate at which my A2 will actually come to beat my A1 will be very, very slow, right, but replacing trace will eventually fix your problem, okay. Correct. So accumulating traces are bad typically if you are doing control, right. It was not that much of an issue when we were talking about the estimation because I was not changing my actions based on this, right, but here I will be changing my actions based on the estimates I am making. So the replacing, accumulating traces are bad, replacing traces are better, right, and you can do a slightly more aggressive version of replacing traces. What do I do in that case? Whenever I revisit a state and I take an action, if it is for all the other actions that I could have taken from that state, I make the trace 0. So I come to a state, right, I take an action from there. So for all the other actions I could have taken from that state, right, I set the trace to 0. That means if there is a specific reward I get by taking this action, that will not go back to all the other actions I could have taken from that state, right. So to see what will happen, suppose I come to S for the first time, right, and from here I take A2, I have not taken A1. So what will be the trace for A1? 0. I am taking only A2, right. So whatever reward I get here, it will be change the value of A2 only, it will not change the value of A1, right. So I want that effect regardless of how many times I have visited state S before. If I visit S, right, and then I take A1, right, then I come back to S after a while and then I take A2 and I get some reward, right. So it is not likely that I would have gotten this reward by taking A1, right, because it is a different, completely different path I am choosing there. So I do not want this reward to go update the value for A1, right. So what you can do is, this is one way of doing, this is accumulating trace, this is replacing trace with 3 conditions. So this is a special case of replacing traces, okay. So you could do the regular replacing trace also, wherein you would have decayed the value for all the other actions, right. This is one aggressive case of replacing traces. So wherever you come back to a state, for that action you set the trace to 1, for the other actions you set the trace to 0, okay. So what will be the forward view for Sarsa lambda? I mean ignoring this part. So what would be the equivalent, we saw the forward view for TD lambda, what will be the equivalent forward view for Sarsa lambda? More or less the same thing, you do not think too much about it, right. So it is 1 minus lambda times lambda wait for the first return, 1 step return, right, and then lambda squared wait for the 2-step return, lambda cubed wait for the 3-step return, and so on and so forth, okay. Do not worry, don't think too much about it. So that is basically it, right. And once you have this ET, so what you do, your delta QT SA will be some alpha times delta T into, right, where delta t is equal to what? Yeah. Okay, and I do not even have to write these things down. I mean, you can generalize directly from TD lambda. Almost everywhere I wrote V of s, I have written Q of s comma A. This I have just done the backward view. The forward view you can likewise very easily write down the forward view for Sarsa lambda. Anyway, good. Any questions on Sarsa lambda? Okay, so what is the next control algorithm we should look at? Q lambda, yeah. It turns out that there are many variants of Q lambda in the literature, right. So, if you read the book, you will get Peng's Q lambda, naive Q lambda, and then you will also get something called Watkins's Q lambda. Watkins Q lambda, that is the one we will look at very quickly, because that is the one that is kind of justifiable, even though in practice it does not work well, right. The other things are just ad hoc stuff, both Peng's Q lambda and naive Q lambda, which will be discussed in the first edition of the book. They are pretty ad hoc, right. I mean, it is not at all clear what they are converging to, and there are equivalently many ways in which you can define a Q learning version for eligibility traces, but Watkins's Q lambda seems to be the most sensible way of doing things, right, even though it is I mean, empirically it can be very bad. Okay. So, if you think about Watkins's Q lambda, what would be the generalization, or just if you think about Q learning itself, what would be the generalization through using eligibility traces? If you think of what we are doing in Q learning, we are taking the immediate reward for taking an action and then assuming you are going to behave optimally thereafter, right. That is why I use the max and take the Q. So, if I am going to use a 2-step return instead of a 1-step return, what should be the 2-step return for Q learning?
Max from the next max state.
I should be behaving optimally subsequently, right. It can't be a arbitrary action. Like in Sarsa I never had that issue, right. So, I could just take whatever action I did, I could just use it, right, that is not an issue, right. But in Q learning it has to be the optimal next action, right. So, we basically have this. Right. So, for this delta is fine, but when I am computing the return, I have to make sure that I am actually taking the optimal action and sampling the rewards, right. So, how do I ensure that? I have to behave greedily. See, I can't do epsilon greedy or anything like that. If I do epsilon greedy, then there is no guarantee that whatever sample I am drawing is going to be from the optimal policy. Well, I mean, there is no guarantee in the beginning when your value function is all messed up, but even as learning progresses, if I am exploring, right, the return I am generating will not be from the optimal policy, right. So, as long as I am being greedy and generating my trajectories, I can use the entire trajectory for Q learning, right. So, if you think about it, what I really need is, okay, I start from S, okay, I take some A, that part is fine, right, I go to some S prime, then what I really need to do is take max a prime, and I will go to some s double prime, and what I really need to do here is take max over a double prime and keep doing this, right. So if you think about it, this is essentially the greedy policy, right. I am just executing the greedy policy. If I execute the greedy policy, then I can use how many ever steps I have gone, I can use that entire return in my updation.
But if we initialize the queue is all from 0, if
Yeah.
we start first, it
Yeah.
will be the same trajectory, it will always follow, because we are not exploring epsilon greedily.
No, we won't follow the same trajectory always, but we have other arguments about why we have to explore, right. We have looked at it all the while. I am just trying to build up why we need to be greedy first, but we all know we have to explore. So we will have to figure out how to adjust that, right. So we will come to the exploration part in a minute, right. But people understand why I need the greedy trajectory, because that is what the assumption of Q learning is, right. I am behaving greedily. So like Shiva pointed out, and like we know from the bandit times, right, we need to explore. If we do not explore, we will get stuck in something that is suboptimal, right. I can't start regardless of, I can start with an arbitrary initialization of the Q values, right, but if I do not explore enough, right, I am going to get stuck in suboptimal policies, right. So I need to do exploration. So how do I balance these two tensions?
So, taking the max has nothing to do with exploration.
Why?
We can just take the max to the next state. We
Yeah.
are not going to that state anyways.
Then your chain gets broken, right, because I want to find the return.
When we were doing Q policy, that was off policy. Like
Yeah.
we were doing Q
Yeah, yeah,
policy, that was
yeah.
off policy. We didn't even bother to take along the trace.
Yeah, that is because we are only doing one step, right. If I am going to take the return, see the thing with lambda is that I am taking some kind of a weighted average of 1 step return, 2 step return, 3 step return, 4 step return, and so on and so forth, right. So one way of thinking about doing this is to saying that I am going to keep track of the optimal action trajectory from every state I have visited. Imagine the amount of memory that you would need, right. I start from S, I take the optimal action, go to S prime, okay, but then S prime I explore, right. But then if I want to use the 2-step trajectory for updating S, I will need to know what the optimal action from S prime is, that I can do. What about 3-step trajectory from S? So what will I need? I need to know the state I would have gone to from S prime, right, and the greedy action I will have to take from that state, right. I will have to remember all of that to get the 3-step trajectory for updating at S. That's too much work, right. As soon as I explore at S prime, all I can do there is use the greedy action from S prime, that is the longest trajectory that I can consider, right, update the value based on that, right, and then zero out the eligibility traces. I can't do anything anymore after that.
Because it doesn't turn out to be lambda.
It does, because as long as I do not explore, if I do not explore for 10 steps, I can use from 1 step return to the 10-step return.
But when we are breaking this trace, then isn't it like we are breaking the eligibility trace?
We are breaking the eligibility trace. That is the main problem with Watkins Q lambda. So the eligibility trace will not run till the end of the trajectory, so it will be only for short periods of time. So that is a trade off that you are giving, that's the trade off that you are taking.
That is
Huh?
that is not even called as a lambda return, is it?
It's some form of lambda return. It's a, if you try to write the forward view of Watkins Q lambda, it turns out to be a very messy expression, because whenever you take an exploration, only till that point you can do the averaging, right. So now what we say is that we do an averaging over all possible n step returns, right, and then all the weight is assigned to the last return, that is what we are saying. So now what happens is, if I can do only up to some say 4-step return, after that I do exploration, so for that particular state I will be doing an average over only the 4 returns, right. The state that came after that I will be doing the average over only 3 returns, because any exploration, all the states that came before me I will make it 0, right, and then the state just before that I will be doing the update for just 1, right. The state just before you do the exploration, for example at S prime, if I take an exploratory action, then S prime will get the regular Q learning update, no lambda business there, right? And I reset all the traces and start all over again. So that is the tricky part with Watkins's Q lambda, right, and the forward view is incredibly hard to write, so I am not even going to attempt to do that, and no, don't worry, I will not give it as homework as well. Maybe we will save it for an exam. Right. So this is my same delta that we have in Q learning. The delta does not change. This update rule does not change, right. So this is exactly the same update rule that you have for SARSA. What changes is this. So if it is the greedy action, right, if the current action is the greedy action, so not A, sorry. If the current action is the greedy action, right, and S and A happens to be a current state and action, I will increment it by 1, okay. Right. So this should be ST, sorry. So if the current action is the greedy action, but that is not the current action, okay, A is not the current action, then I decay the eligibility trace of A, I do not add a 1, right. If the current action is not the greedy action, I zero out all the eligibility trace regardless of what state, what action, everything. Is it fine or should I do something else?
How is this exploding?
Hmm?
How is this exploding?
What is
Why
exploring?
am I exploding?
This is the exploring part. I have not written anywhere about action selection, right. So when you are doing the action selection, you do it in the epsilon greedy fashion. So whenever you actually pick an action that is not the greedy action, that 1 minus epsilon times, you make this update to the eligibility trace. If you have picked the greedy action, then you do the regular accumulating trace update here. So likewise you can write one version for replacing traces as well, right. Or if you want to do Dutch traces, you can write one version for Dutch traces as well, Dutch trace version here and a Dutch trace version here. So you could do all of that. Okay, make sense? So the main problem with Watkins's Q lambda is all the traces will be very short, unless you decrease your exploration by a significant amount, right. If you say I will explore with say epsilon of 0.1 or something, then 10% of the times you are going to take exploratory actions, right. So things can get very, the traces will get chopped up a little, right, and you lose the advantage of doing eligibility traces, okay. No, so here is a picture that they have. Maybe I should draw this on the board. Okay, let me try and draw this on the board. Easy enough. Okay. So that is the final state I am going to get to okay, and that is a reward, let us say some reward, say plus 10, everywhere else it is 0, okay, and I have say gamma of 0.9 and lambda of 0.9, okay. So I am doing some random exploratory trajectory, I go something like this, I reach there and I reach the goal and I get the reward, okay. If I had been using regular Q-learning or SARSA, if I had been using regular Q-learning on SARSA, which are the states that will get their values changed after one trajectory like this, online Q-learning? So this guy alone, right, this state alone, the value of this action will go up, right, value of that action will go up. So what happens with TD lambda or Q SARSA lambda in this case?
All the states from
All the states, so but unfortunately,
stop when we started exploring.
no SARSA lambda. Probably it will stop somewhere there. So this decays to such a small value, after that I do not update it, right. So unfortunately you are getting wrong updates, right. The right action to do here is to probably go here, but the point to note is with SARSA lambda, with one trajectory I update, I know something or the other for so many states and actions. Well, if I had done just plain SARSA or plain Q learning, it would have been just for one step, and that is one of the reasons we expect this to converge faster. Just to give you a very rough intuition as to why you expect this to converge faster. This intuition comes from the backward view, right, because I am updating in so many states, okay, good. So there are a couple of other things I am debating whether I should talk about it or whether I should make you guys read about it, okay. So what does Q learning do for us? We keep calling Q learning as an off policy learning method, right, but it really does not fit into the structure of off policy algorithms that we saw in the Monte Carlo chapter, right. So we said we had one behavior policy and one estimation policy, and we are trying to estimate the policy by behaving estimate the value of that policy by behaving according to another policy and so on and so forth. Here we took a lot of shortcuts because the estimation policy was the optimal policy, so we try to take all kinds of shortcuts, right. First of all, we do not know what the optimal policy is, right. In the typical off policy learning we talked about, we have a pi and a mu, and then we did all of those things, right. Now we do not know what the pi is, we know what the mu is because mu is what we are behaving according to, but pi is the optimal policy, I do not know what pi is. So really Q learning does not fall into the off policy mechanisms that we spoke about. So you could think of having a off policy version of TD lambda, right. So I could have a pi which I am trying to evaluate, but my trajectories could be coming to me from some mu, right. So how do I handle that? So showing the equivalence of SARSA and backward and forward view of SARSA lambda, you still have to assume that you are doing this offline, not online. So at the end of the trajectory only you are changing the values, okay, and that becomes very tricky. You would never ever be running SARSA offline, right, because you want the values to be changing as you are executing so that you start learning, right. So you do not want to be executing random trajectories and then, so it becomes a little tricky. So there are more recent works where you can have an online version which allows you to, which gives you equivalence between the online forward view and an online backward view. Anyway, that is an aside. So let us go back to off policy TD lambda. So what do you think we should do? So we basically have this, right. right. So, that is the right. So, that is the update equation, right. The other one is gamma lambda E t minus 1. So, I have to somehow figure out how am I going to insert my importance weight into this, and I have to figure out how I am going to insert my importance weight into this. How do you think I will insert my importance weight into this?
Directly multiplies.
Huh?
Directly multiplied with the previous
So, let me define something that make my life a little simpler. I am going to define rho t of S as, right. So, whatever means the pi S of whatever action I took at that time. Yeah, that is a good point. So, I do not need to, so it is rho t is the importance weight at time t, it is for that particular choice, right. So, at that time I made this choice, right, I made a choice between some action at time st, state st, I picked an action, right. So, what is the probability of me picking the action? If you remember our expression for the importance weight, right, we wrote it as a product of pi st at summing over all t, right. So, that is essentially that item, that is the entry I want. So, rho t will be pi st at divided by mu st at, and that is that one term from the importance weight. If you actually have notes, you can flip back and look at the importance sampling thing that we talked about, right. So, I basically multiply this by rho t, but the question is, what do I multiply by rho t? Just the gamma lambda E t minus 1, or should I multiply the plus 1 also?
Depends.
Right.